So let's start the exercise 3 tutorial. So this exercise is about system responses and also the signal spectrum. So this exercise, actually, first one, you will have this kind of system, which is quite similar to what you already analyzed on the second exercise. There's a block diagram, and then we just have different values there. Actually, I think you should open it up to see all the values. So there you have the SSS. Your own special number is actually defining these 4 decimal digits here. So it's 1 point your number, and this feedback term is 0 point your number. And then there's a minus 0.65. Okay, that kind of system. And the drill is the same as yesterday's exercise, so you just need to analyze it to find the system parameters, B and A, for this system. And then you would do the stem plotting of the impulse response, and from that impulse response, you should be able to define if this is a finite impulse response system or infinite impulse response system, and of course with the justification. Then next one, set up the sampling rate for the system. So this is just a block diagram with no information about what is sampling rate. Here you set up the sampling rate, and then basically plot the frequency response, which has the frequency response always has the amplitude response and also the phase response. And basically from those pictures, you should be able to say if this has linear or non-linear phase response. Okay. Next one, zeros and poles. That's always interesting. And then basically a question at which frequency the system has highest attenuation. Highest attenuation would happen on this frequency where you have the zeros on it. Okay. Then the group delay. Okay. Hopefully this group delay function exists in our signal toolbox. I think it does. If not, then it's not the big deal to actually make your own group delay function. Then 6, scale the system such it has unit gain as passband. Remember one of those animations, when you move the poles close to the unit circle, you start having gain on the system. It's not unit gain anymore. So you don't necessarily want amplification of signal on a filter. So that's why it's very useful to actually know how to scale the filter so it has unity gain. Then basically that ends the system part, and the next would be the system analysis part, and the next 4 are, well, next 3 questions are about the generating a sound sample. So it has a actually chirp. This is going to be fun. Chirp signal, meaning a signal which has a varying frequency. It has variable frequency. Starts at 200 Hz and then ends at 1.2 seconds at frequency 3500 Hz plus your special number. Then add some random noise with okay, again, signal to noise ratio, decibels. I know. I'm ill. The engineering decibels here again. So you need to do the similar calculation what you did on the first exercise, and then calculating the power spectrum of the last points of the data set. So what does the power spectrum looks like for the last 2048 data points? And okay, and then we have part 9, which is the spectrogram of this chirp signal. So that spectrogram is a graphics where you have the time on the horizontal axis and frequency on the vertical axis, and it shows the how the frequencies are changing. So there you should see the chirp, which is actually linearly increasing the frequency of the signal from 200 hertz up to the 3500 plus SSS hertz. Okay. And then part 10, basically combining your system, this system, and filter your signal using that system and see what happens. Okay. So where shall we start? I should probably start Octa. And this time I actually started already on morning, and also just to wake up the graphics, I also put the run plotted something. So now everything should be good. And I could actually, just for fun, I will take yesterday's system. I think I had a one system here. Okay. Wait a minute. Let me go to that directory and okay, so these are the commands from yesterday. I just want to have one of those systems. Why on earth? Oh, okay, I see. All right. Now I see all the parentheses here. Okay, we had this system here starting from line 61 here. A's are 1 minus 0.50 and B's are that. Actually, if I take, let me take this system. Okay, if I just, paint it and do run selection. There we go. So I'm actually now dealing with this system. This is from yesterday's history file. Okay, just an example. So what I did actually, what commands there are right there. Wait a minute. So A equals to 1 minus 0.50. B is 1 minus 0.51. Then I calculated the roots of both, so zeros and poles. Did the zero pole plot. Then I decided to change one of those poles, and then put the complex conjugate to it, and then I have. So this system actually is looks like that. Okay, zeros and poles. The filter coefficients for that one are now, okay, let's see. BB is 1 minus 0.5, 1, and AA is that AA2 here. So that's the system coefficients. for my example system. Okay. Next step would be to check what is the impulse response. Yesterday we already checked that we have this filter which actually is the arbitrary response of any system. So you're on the filter, or if you have a system, maybe I should actually turn this one the other way around. All right, there. Okay, so now we have that system coefficients. We know A and B, or actually AA2 and BB. So for that system, if you have a input X, output Y, then basically this on octave or is same as Y equals to filter BB AA2 XX. So for any input you can calculate the output that way. Meaning that we can actually calculate the impulse response by feeding in the delta function, and what comes out is the impulse response. Good. There we go. So let's calculate the impulse response then. First we need the impulse. And for impulse we need the indexes, the point of interest actually. I usually start from negative values and then let the impulse go long enough. How long it should be at least? At least the length of your system. So basically you should let the system stabilize at least the order number much. So you find the highest polynomial coefficient, non-zero polynomial coefficient on the system. So basically that's enough to wait for impulse response to stabilize. So let's put it like this. So if you have an impulse response, for example, like this, and you will wait until the order number of the system. If it stabilizes, so that basically after that everything is zero, then it's FIR. If it doesn't stabilize within n values here, then it's IIR. In this case, it would be IIR because that's non-zero. But if you had the order number up to here, well, actually, up to here. Up to here, then this is FIR because all of these are zero. That's how easy it is. So for, say, practical systems, they are usually the order numbers are less than 8 or so for filters. Or you have subsections of second order systems. So it's enough for me to calculate only that much. My order number is 2. Second order. 3 parameters on numerator and denominator polynomial starting from the 0th order polynomial. Okay, so this is the region of interest. There, and then the unit impulse function, simply nn, test if n is equal to 0. Okay, I noticed that on the first exercise, a lot of you actually did the impulse by basically subtracting or checking the this number is less than equal or and greater than equal. Well, I think the problem was there. I didn't point out that the testing the equality is equal. Same as in C language. If you have the single equal sign, it's the setting of variable value. Exactly the same also in C language. Okay, so this is our impulse. So the impulse response, H, equals filter BB AA2 DD. And we can then stem plot that one like this. Obviously this is IIR system. To be sure that it's IIR system, you can always, do also the calculation, like calculating the norm of impulse response values where nn is greater than the order number 2. If this is 0, then we have a FIR. If this is non-zero, then we have a IIR system. And definitely this is IIR system. Not even close to 0. Good. Close to 0 means e to minus 10 to minus 12 at least with the computing accuracy. Okay, so this system is IIR. Okay, next step. Next step would be to calculate the frequency response. And for frequency response to make any sense, we actually need to set up the sampling time. And okay, just for fun, I will mark a sampling time of 1000, which is 1000 samples per second. Say this could be not an audio source, but or should I make it audio filter? Okay, I will make it a for audio filter, since we have this audio signal later on. Okay, the CD quality audio. So that's the sampling rate. Now I'm interested about that system. What is the frequency response of, let's see, stem? No, stem. C plane. Of this system, what is the frequency response? Okay, and frequency response actually, it's easy to calculate. There's a function called fetch. BB AA2. Same way parameters as earlier. The third parameter is how many points you are calculating between 0 and Nyquist frequency, the sampling rate over 2. So this would be 1024 points. Something, 2 to the power something would do just fine. If you have a less points than 100, then it looks funny. The picture looks like lines. With more than 1,000 points, then I don't know if you gain anything. So it has just more points, but it still looks the same. So this is simply a graphical. So this basically just sets up. Okay, when we have this, think of again the complex plane. Now we have the system was looking like this, something like that. So think of that as in how many points in unit circle you want to calculate the frequency response. So basically, how many points here will be mapping in here. There. And then the sampling rate, the fourth parameter. You can take a look at the help of flex. It says probably the same thing. Wow, that's nice. That's actually that's a pretty filter. Let me put another figure here and put the Z play. What happened? Ha. Oh no, I think I broke my. Now I know what was going on. Yep. Oh. Figure and then C plane. When you call figure, remember the parentheses. Otherwise, it does give you some funny messages. There. All right. So now we have these two figures here. So on the right hand side there's the frequency of the complex plane, zeros and poles. On the left hand side we have the on the top figure there's a magnitude response, and the bottom figure there's the phase response. Okay. So what we can tell. It's not the best. It's a low pass filter, but it's not the best one. Let's take a closer look at the frequency of this magnitude response, and let's see how do I can. Wow, something funny happened. Flex BB AA 224 and FS. Okay. There we are again. So this picture here. So basically we have just that it looks like low pass filter, but okay, that's at 0 dB, and we have just a signal gain up to 10 dB on the passband. So yes, it's a passband filter, but it has some extra gain on it. So that's one problem. It's not unity gain system anymore. We need to fix that gain somehow. But on the other hand, when you're looking at that one, and remember still the one of those slides. Let's take a look at those slides again. Where's my slide? So okay, there. Okay, there. That one. Ah, of course it doesn't show up here. Frequency response. There. That was a 4-point the 4-point running average filter, which had the same amount of stop band attenuation. But look at this one compared to this one here. So we actually gained almost flat passband compared to just this simple simple 4-point running average. And okay, so that's what we gained. What we lost, though, was the linearity of the passband linear phase response. On this 4-point running average, you have a linear phase response, meaning constant group delay. But here we have the actually group delay will be a little bit warped. It might not matter, but well, this is analysis of the system what we created. Okay, so that's the frequency response. So from this point, you can already say this is nonlinear phase response. And you also can see there is some good things happen also for the stop passband. Let's next analyze the group delay, but for that one, I think I need to Google a little bit. Octave group delay. Compute group delay. Oh, GRP delay. Maybe not. Maybe yes. Let's take help. Help GRP delay. Group delay. Oh, excellent. We can still calculate the group delay with just the parameters B and A. And we want to do it so that we can actually put there also the number of data points, yes, but especially the sampling rate. So then we know the group delay in seconds. Good. So let's try that one. So just to make on safe side, I'll make this like this. Group delay BBAA2. Well, I think 512 points is just plenty of points for this plot. And then just like that. Now I need to go back to that help. Do I have the help somewhere in here? Ah, okay. So if I don't put there the okay, and if I put the sampling rate, then it actually gives the physical frequency. Okay, that was the thing I was looking. So WW now is the actual physical frequencies. Let me change this variable name. just to make sure that it's not mixed with, you know, the omega, the angular rate. So there. And now we can plot as a function of f the group delay on new figure. Ha! There we go. So we started from the 0 poles, then calculated the frequency response, and now we have the group delay. That's nice. I think this gives the group delay in samples. I'm quite sure, since 3 seconds sounds a little bit long for any filter. So this group delay is in the unit is how many samples. Otherwise, it doesn't make any sense. Although the frequencies are in physical frequencies. Well, whatever comes free doesn't have any guarantee. So on MATLAB, this function would work differently, and it would be more obvious. If you put there physical units, you will always get physical unit outcome. Okay, but this is in time steps. About 3 time steps difference for that frequency. So it comes out from the system 3 time steps later than input, and basically we can see from here the lowest frequencies are coming out from the system faster than this 5000 Hertz signal. So this comes actually 2 time steps later. All right, so that's the group delay. The next, and actually the last point on this analysis, is to fix the gain of the system. So how to fix the gain so that this will be unity gain system. So scaling the filter for unity gain is quite simple. Let's take first help on Fretch. So we already calculate the frequency response. Okay, how about if we calculate the frequency response again, and we actually get the value of it somewhere? So there's the frequency response complex as a complex numbers, and I think this would be also the frequency in Hertz equals Fretch BBAA2 1024 FS. Okay, there we go. And H is 1024 points times 1 complex number. So that's the complex spectrum, meaning that's the both amplitude and the phase response as numbers, not the plot, but the numbers. So basically, that's the values of this picture in complex numbers. And then we have the frequency, but to scale the filter, we just take what is the maximum of absolute value of HH. That's the maximum gain. And maybe I will just put that one as the variable C. So that has about 3.16 is the amplification of that system. meaning if I divide the system parameters by this number, I have actually unity gain system. So let's see. BB parameters were 1 minus 0.51, and then AA parameters 1 minus 1, 0.5. In order to keep the calculations correctly, we cannot touch the Y parameters, basically. Well, we can. It would calculate it correctly, but as a matter of fact, you really want to just divide the system input with this number. So basically say BB2 equals BB divided by CC. So this is the scaling for unity gain at a pass band. And frequency response of this system. So we just modified the forward parameters. Where did it go? Oh, that's the without. That's the without the scaling. Okay. Here left we have the unscaled system, and on right we have the scaled system. And now it has the maximum gain of 1, meaning 0 dB. Ha! Wonderful. We have a low pass filter. Good. No, I destroyed the destroyed that FF. But anyways, so what happened? So okay. Just to summarize, so we have this system, zeros and poles, the frequency response for that system, then we have the group delay calculated, and then we have the final step, we scaled the filter so that the maximum gain is actually 0 dB. Okay, good. That's all there is for. Oh, yeah, and actually we also have the impulse response, right? I forgot that one. So let's put another figure there, add there the impulse response. Stem. Okay, there, the impulse response, which says it's IIR system. Good. So that's the full analysis of this system. There's nothing more into it. So based on this one, you can go and do the exercise 1 to 6. All right. Next, how about the signal spectrum? There are two ways of calculating the chirp. One is the easy way, you just call function chirp. Yeah. So chirp with time vector, sampling time vector, frequency, starting frequency, and then a couple of other parameters time t1. Strange. Vector of time t1 chirp, frequency at time 0, time t1, frequency at time t1. Okay. So basically you can just call this function properly to produce that chirp signal for that exercise there. Or I will show you another way, since this is the this way you can actually understand better how to generate all sorts of frequencies. Let me first take a picture of that one, and then I need to explain the whole thing on the whiteboard first. So basically what I'm going to do, I will be showing you the whole essence of frequency, what it actually means. Okay, another one of those. They are whiteboard markers. Red doesn't come off that easy. Okay, so if we have a sinusoid, 2 pi f times t, that actually ends up being a one single frequency in frequency domain. One single frequency, or if you sample it has the envelopes here, but anyway, so that's simple. But how about what is the frequency of this one? What is the frequency of this signal here? Hint. The frequency here is f. It's multiplied by then by t. That's the generating polynomial. So basically, the frequency of that let's yes, t. That equals actually dg t over dt. See, if you derive this one as a function of t, then basically you get just that constant f. So if you want to have the frequency, and that's time now, and if you want the frequency go like in ambulance, for example, like this, what would you do? So this is how you want your frequency to be. This formula requires GT. How to solve GT from this equation? There. We could actually try that one. So if we have, for example, a signal frequency, really obnoxious 1 kilohertz signal, and you want this frequency amplitude to be, for example, 500 hertz, amplitude sign here, and this be, for example, the base period, say 0.5 seconds, meaning okay, that's the full. Okay, so that means the okay. not that frequency, but the other frequency. How to mark it? So would be let's mark it f prime equals 1 over 0.5. So that would be a kind of really nasty sound. Right. So basically what we will do, it will generate something like that. Hopefully. Okay. The easier would have been, of course, to take the chirp, but I don't want to make this exercise for you. You need to work out the exercise. This is the easiest way since we have that chirp. But how actually this kind of the generation of any kind of frequency shift or frequency form would work out is by that method. All right, so back to another view. So see, so we want to I think it's undulation. It's the correct between 500 and 1500 hertz at rate twice a second. All right, good. So first, a generating polynomial. Let's make first the sample time vector. So from 0, I will make 1 over fs. That's the sampling time, and make a 2-second long time vector, for example. 2 seconds long sample at rate 1 over f. At rate fs. Good. That's just a time scale. And our frequency f would be then f. How many f? 1. Okay. Would be that 1 kilohertz plus sine of 2 times pi times 2 times per second times tt, and this has an amplitude of 500 hertz. And like that. Good. Let's see, does it look like that? TTFF. Whoa, what happened? Not FF. Sorry. TT and F. There. Okay, it's pretty good. Okay, it's just the, it has an offset of 400 on this plot. But anyways, it's 1000 hertz, and then it goes on the both ways, the 500 plus 500 minus 500 in, 2 cycles per second. Good. And next we will integrate. And just to make sure, I will try to find an integral. Function list, do I get the, maybe I'll just, integral. Numerical integration, good. Functions of one variable, good. We actually need a cumulative integral. This quad actually just gives one single number, but I think cumulative integral gives you since you need one value for its data set. So basically, at this point, you have integrated up here. So G at T1 here is actually this integral. If you are G at T2 here, then it will be integral up to this point. So it's a cumulative integral what you are looking for. Let's see. Kuluma. Cumulative integral. Okay. Cum traps. That's one numerical integration method. You just give x and y. X is the time and y is the data. All right, so our G, well, now it's just simple G. Double G I already used. G equals cum traps of time and frequency. There. This is the generating function for sine 2 pi G. Okay. And now finally our signal would be SS sine 2 times pi times G. Wow, that was a lot of work. And it sounds like this. Should I turn on the... Okay, no, I don't want the headset. Speakers. Set up the speakers. That was fun. So much fun. Even faster. It's so much fun to generate your own sounds. It makes me happy. I know I'm small things makes me happy. All right, so now we have a sound signal to test. Your test signal will be a chirp, and of course you need to also generate some noise just for fun. Let's generate some noise for this one too, just for fun. So this time I will just put there some arbitrary noise. Let's see, at just linear amplitude of 0.1. You will do decibels, of course, but today. But I'm lazy. I'm just putting here just the standard deviation I want from this signal. Okay, but I can actually also calculate what is the signal to noise ratio here. So basically, signal to noise ratio would be 10 times log of 10 the variance of signal signal without the noise divided by variance of noise without the signal. There. So signal to noise ratio of 17 decibels. Okay. Works with me. Signal to noise ratio was that 17 dB in this case. Okay. Next step would be do some spectral analysis. This data set has very it's quite long. Actually, it's how many data points? Wait. 88,000 data points. I don't feel it would be any good idea to just do the analysis of the full data set. Let's take a quick look on. Okay, let me plot that one again. And let's try to analyze, say, data points from here to there. So that would be, okay. Time values from, no, it doesn't make. Okay, just around the half second, say. And then take, say, 1024 points on that one. So I will take a subsample. And then I'll select 1024 points long. Okay, how to find that value? Well, we have the T. So basically what we can find is the okay, how to make it easy. Okay, yes. So if we multiply 0.5 times our sampling rate, that's about where the half second is, right? So this is the index II. So it's my subsample will start there. First sample. Let's see. Let me take that one out. So I'll see. Okay, 20. Yeah, that makes perfect sense. So that point 22,050 would be our first sample point, and then I will take 1,024 data points, meaning okay that my spectral resolution would be something. Okay, let me worry about that later. SSA, like subsample. SSN starting from point II, and then we'll just take the 1 to 1024. Okay, this is a neat trick to actually just take one point and then take the next 1024 points out of that. You can also start from the end and take the previous data points. Then you probably want to subtract those values from the data points. For the spectral analysis point of view, it doesn't make any difference which way your index is going. It's still the same. But that's my region of interest here. And I will start doing the spectral analysis, and that's very simple. FFT SSA equals FFT of SSA. So I just make brute force fast Fourier transform, and that's why I also picked the 1024. It's a power of 2. Fast Fourier transform, and then basically I can calculate the power of power spectrum of SSA. Let's say PSSA is that FFT SSA times the complex conjugate of FFT SSA. That you have learned already from Aoki. So that gives you the power. And then it looks like this. Something strange. Why I have do peaks there. I have 2 peaks because of this Fourier transform actually calculates the signal spectrum for the full 2 pi circle, meaning basically that at the middle you have already hit the sampling rate over 2. But it's a full spectrum. It's required to reconstruct the whole signal. But for amplitude or phase response, the spectrum point of view, you don't need more than the first half of the picture. Okay, so we need only let's see, what would be the good variable name? II is already used. Okay, ins. From the first to 513 is the last point. So first point is actually a frequency of 0. So basically, you take, if you take this one in, you also have to take these middle points in, and that's exactly at Fs over 2. So my frequency scale for this one, FSC, is actually so from 0 to 512 points. I had originally 1024 points. 24 points on my Fourier transformation, and this is then multiplied by the sampling rate. So this scales actually my this first half of these values in between 0 and sampling rate over 2. There. Or, well, the correct way actually to do it would be ins minus 1. Okay. There we go. So now I can actually plot FSC PSSA Y. Sorry, of course, ins. Same length vector. So this is just the first half. And this is also, as you can see, it's a linear scale, not too nice. Did I actually use the noise data from my sample? Yes, I did. Good. So another thing is that is now still a little bit awkward is the Y scale. when you have power spectrum, you should use actually the decibel scale there. Otherwise, linear scale does not make much sense on the power. So, okay, dBPSSA is, okay, what is the multiplying factor here? 10 or 20? If I calculate the decibels here. 10, that's already power. 10 of PSSA. Power spectrum in dB, unscaled dB. All right, now we can actually dBPSSA calculate and show the power spectrum. Ha, that's perfect. It shows the peak around 1000 Hertz, but okay, it looks a little bit wide, as it should look, since this frequency is always changing here. If it was a fixed frequency, then it would be just in one place. But my frequency is now all the time changing, so it's actually spreading the spectrum. Okay, so if it was a single frequency, then it would be a higher peak on that one, but now the single frequency is changing. Now we have a kind of bell curve or something like that. And you can also see the noise floor here. So basically all of that is noise. It's wideband noise. We had pretty good signal, which had the 17 dB signal to noise ratio. And when you calculate the noise ratio, actually this could be used to estimate the noise ratio. But then you of course need to integrate over the full power. What is the integrated power of signal here, and you integrate the power of the noise here. So good. So that's a simple single spectrum, but this is not the whole figure or whole picture of the stuff. So since basically this it doesn't show how the frequency varying, and that's where this spectrogram actually comes into handy. That's the almost the last page here. There. So basically, spectrogram would show how the signal frequency is varying. So this is a time, this is the frequency. If we have a chirp, it starts from, well, at some point in your signal, it starts at 200 Hertz and then grows somehow. But anyways, this is a color-coded image showing where are the spectrally interesting things on the signal. Alrighty, so let's go back to Octave there. So final part, or almost final part, is the spectrogram. Now I need to take a look at again on the manuals. So how to actually, what is the function for spectrogram in Octave? Specgram. Okay. I've also done some things here, but my point here is I'll try to find out if they have this. Well, we'll see. I will complain if it doesn't work right. Since there are historical reasons why the some of the spectrogram subroutines are by default showing wrong kind of spectrogram. So it's just annoying to see that time is actually going wrong way. So in one of those programs or subprograms, there is time that is actually starting from here and going up like that. What? That's not engineer's way of doing it, but okay, let's try the spectrogram in any case. So spectrogram was the function, and with that parameter, it should actually plot a nice spectrogram for us. Well, I'll do another figure, new figure, and just say spectrogram, and let's see quickly. Data, how many points, sampling rate. Okay, that in that order. Data was SSN. N. Signal is chopped into overlapping segments. Okay, so if we have a signal, where do we put that? I already had it on Monday, but anyways, it's the spectrogram will actually take a certain number of signals here and calculate the Fourier transformation of that, and then move into next one and move into next one, and makes that image. So we need to set how many samples we have on this one. We had in total, we have 8,000 samples. I think we can use, for example, 512 would be our 512 subsamples. Yeah, let's try that one. We can always fix it. Then we know our sampling rate. Let's put it there. Then the next parameter was window. What is the window size? So we can actually go a greater window size than that 512, or smaller, not smaller, but greater window size as 512. For example, if you want to have the samples so that you have, say, not a number, not to the power 2 number samples in each section, that'll be fine. Or yes, but as long as you use the number samples you are having the FFT on, that will be power of 2, and that would be that number. Okay, but window we are looking at can be different. I have no reason why I would use that. Okay, so that variable should be the same as the number of data points here. Then the next parameter, preferably half of the previous. So this is the overlap. So do you take zero overlap, or do you actually make the halfway overlap? Halfway overlap works on the most cases, meaning the next one starts right here. Good. And we have a spectrogram. Wow, that's cool. Hey, it looks like that one. So we had that 1 kilohertz, and then we have the 500 hertz, plus minus 500 hertz undulation there. All right. If you want to earn extra points, try to make smiley face on spectrogram. and hear what it sounds like. And make it your, mobile phone ringing sound. Yeah. Okay, but it's doable. You know how to generate different forms. So what is smiley face? Two signals, one going that way, another way that way. Frequencies. And then, of course, you need the eyes, same way, and so it's just these arcs what you are producing for the on the spectral plane, and then thinking of how to make a function that generates the frequency. Yeah. Now you can't sleep for next 2 weeks. Oh boy. Yeah. So spectrogram, and then I also have the spectrum somewhere. Yeah, single spectrum. That was done somewhere here. So as you can see, the spectrogram had the frequency of 0 to the Nyquist frequency, and it also shows from 0 to 2 seconds the whole data set. You can play around with these values basically. Number of points in FFT actually defines the spectral resolution. In this point, I had 1024 samples in my Fourier transformation, meaning that my spectral resolution would be about 43 hertz. So that's how what separates each point on that spectrum. In here, I actually dropped that number to 512, so it would be about 86 hertz resolution. But on the other hand, it has a lot of data, so okay, what is the correct value on that one? You eyeball it. When it looks nice picture, this is graphical presentation. It has no other scientific meaning than what is on the eye of the viewer. And what is the old saying? Beauty is in eye of the viewer. Same thing actually here. When the parameters for this spectrogram are correct, then it looks nice. Okay, good. So basically the last part is the very easy part. Just a reminder, we have this signal SSN, and we have the system BB2 AA2. How about filtering the system with our signal? With the system preferably. Okay, and this is very simple thing to do. So SSO, like SS output, would be filter BB2 AA2, and then we SSN. I'll just, play here. So, yeah, actually, since we have the spectrogram here, so why not to also show the spectrogram while we are at it? So that's the data of the filtering. Let's compare it with something. So that's our system amplitude and phase response, and that is the filtered data. So we have this notch where we have a lot of attenuation showing up as dark line here. Otherwise, it looks like, this, well, compared to the original, actually, I think also this should be darker, meaning this is low pass filter actually has attenuated a little bit of that noise there. Okay. Otherwise, this looks like it is not touched. So, but well, seeing is believing. Let me put another figure here. And then the spectrum of the original. That one. That one. Yeah, maybe. Can't say really. They don't have exactly the same color coding. Because of that, actually goes as the darkest color. Here's a different value is the darkest color. But okay, so this here is darker than that area. But in here, this is as dark as here. So it means that there you have that effect. Stop band attenuation. Not too much, just 10 dB, but still. Wow. So that's my show. Now it's your time to shine. So start working hard on exercises. Thank you.